I think today begin. Payal has set the correct tone that it is a very empowering software that you are learning today. Um, some of you don't know CFD, some of you know some part of OpenFOAM. So it's a very mixed crowd. But right now we are going to view you all as same. And you can see that from each of your uh, own at your own pace, you can quickly learn this software. Okay, it's not too difficult. But one important point I would like to emphasize is attention to detail. So that becomes very, very important when you're trying to learn OpenFOAM, trying to understand CFD's application and how you can use OpenFOAM to enable yourself, either whether it be starting a company, starting a new job. Nowadays, companies like GE are all moving towards. Of course, they use some part of their work to be commercial software based, but there is initiative to move towards OpenFOAM. And the applications in industry are not easy. So very quickly, the industries want people with a good grip and understanding. It is not like you've done the tutorials of OpenFOAM, and that brings you to a point, but you should also understand it. Now, why am I saying all this? In today's workshop, all of this today, you will have to, I expect you to ask questions, to have complete focus in what is being shown to you, because you have experts, the OpenFOAM team in front of you at your full disposal, if I have to say that. So I want you to fully utilize this opportunity to express your questions. And, the focus has to be learning OpenFOAM, learning CFD. Okay. So with that, let us quickly jump into today's first session. I'm not going to show you OpenFOAM, but my job here is to first bring everyone onto the same plane of very quickly understanding what CFD is. Okay. And I do understand that a few people have already gone through a CFD course. So I will seek your help in trying to fill the gaps. Okay. Let's get started. CFD. Okay. So things are written in front of you, but I would like people to, you can unmute yourself and answer, right? CFD means computational fluid dynamics. Okay. So the question is, I'm going to solve a set of equations, right? So does anyone know what are those set of equations? You can talk and interact out loud. The common set of equations that I will probably use for a CFD problem, a fluid dynamics problem.
Continuity, momentum, energy equations.
Okay, all right. Anybody else?
Navier-Stokes equations.
So Navier-Stokes equations. Okay. Anyone else?
Like if there is heat transfer is also involved, like some heating plate is there, so we'll be solving energy equation also.
Absolutely. There is a choice. If it is a heat transfer problem, you would take an energy equation. Otherwise, you will not. I think there are versions of compressible and incompressible equations.
Yes,
yeah. Anyone? Any other inputs you guys can give me?
like it could be multi physics problem also, like some apart from fluid flow, there is like electrical, like say if there is ionic fluid is flowing, so that will consider electrical equations to be solved, like Poisson equation maybe.
Right. So essentially, what you're saying is, I have fluid flow, but maybe I have something else happening other than that. Maybe magnetohydrodynamics, because you're trying to find out how you can probably move a particle using magnetic force. So you have to solve an additional equation. But everyone is right. So there is this standard set of equations, which is conservation of mass, conservation of momentum, and maybe in some cases conservation of energy. I think that is the fundamental laws we're looking at. And when we're trying to solve equations, we have to satisfy that. Okay, so maybe conservation of momentum is something we will take. And well, I know this very famous equation called F is equal to ma, correct? So mass into acceleration, and typically that's from your Newton's law, correct? But I do know that the Newton's law applies to, say, an apple, right? So mass times the acceleration. So typically, in proper technical terms, this apple is called a system, right? So it is mass times acceleration of this system. Okay. Now the problem is when I'm talking about fluid dynamics, right? Now I have to apply this conservation law, conservation of momentum, to a fluid, and fluid keeps flowing about here and there. Now, how do I look at every particle in the fluid, or do I look at take a bucket and carry it around? Or what do I do? Any thoughts on that?
We define a system to analyze the entire system. So, I mean, behavior of the person.
You'll have to be louder, Prithul. I couldn't hear you very clearly.
Sorry, ma'am.
Like we can change our approach from here. Like if, as you mentioned, if there is apple which is like moving around, so in place of that we have fluid with millions of particles. So
Mm-hmm.
instead of considering a particular particle, we can consider a domain.
Mm-hmm.
So from there, different forces, and maybe we can define the acceleration term of there only
Okay.
by,
Okay.
as you mentioned, in the Reynolds transport theorem.
Okay. So see, so to put this question in perspective, now either I have an option of tagging a bunch of particles and traveling with the particles. So I'm tracking in a way the particles, which is largely the Lagrangian frame of reference, which is kind of written on the screen for you. And the other part of it is called the Eulerian. Now, what does the Eulerian do? It says that, listen, for complex problems, I am not going to be following along the particles. What I'll do is I'll stand at a point and I will create a window in front of me. Okay. And I will see this particle or this, what happens to a bunch of particles as it enters my window and it moves out. Right. So my focus is going to be this small volume space in front of my eyes. And that is called the control volume. Okay, so the whole procedure is to look at several such control volumes at different points in space and come up with an understanding of what is happening to the flow. And that's called the Eulerian approach or the control volume approach. Okay, so the question lies, okay, I know that there are these systemic laws, F is equal to ma, where it's a solid apple which is moving around. And I now have a fluid where I say, okay, either I travel with the fluid or I create a control volume, like a window in front of me. And a large set of problems are in this control volume approach. So we'll be talking about the control volume largely in this case. So when I have the control volume, now my question is, okay, fluid is coming in and moving out, but how do I apply an F is equal to ma to this control volume? I don't know how I'm going to do that, right? So that's where you have something called the Reynolds transport theorem, where Reynolds proposed how to change this systemic law of conservation to, a conservation within a control volume. Okay, how do I define fluid is coming in and going out? How do I talk about conservation, right? So that's happening through the Reynolds transport theorem. Okay, so the first line here is the Reynolds transport theorem. Okay, anyone want to venture out what these two terms mean on the right hand side?
Like it's a conservation across the, like for the first term, it is the some quantity n which is coming inside, like which is changing inside the contour. First term, in the middle, which is like how that property is changing with time over the control volume, and this last term is like by what flux the quantity is like either coming like net transaction of the quantity with the control volume.
Okay, good, good. Anyone else wants to venture and say something? Okay, that's fine. So essentially what we're saying here is in a control volume, I mean, it looks all scary math, but it's not, right? So there is this control volume, okay, and I'm looking at it. So all that I'm saying is, listen, I'm going to have to try and see the change that is happening in this control volume. That's all that I have to do. Now, this change in this control volume equals to, if I have like some kind of, imagine I have a smoke generator within this control volume, and there is also smoke in and around, okay, and fan is blowing in. So within the control volume, because there is a smoke generator, smoke is going to get generated. So I'm saying change in this property called N over time within the control volume, CV, right? So I'm just integrating, saying over the entire control volume for a time, how much change. So something gets generated over time, there is a change. Plus, that change will also include if some external smoke comes in and goes out, correct? So the net amount of, if I have 100 as a number at a time, that 100 could be a sum of what gets generated per unit time inside plus what comes in and goes out. If 20 comes in and 30 goes out, right, there is some amount of generation. Net amount will be some summation of this, right? So that's what this equation says. This equation says that an overall change in a system, okay, N is that quantity, is equal to whatever is changing in the control volume plus whatever comes in and goes out. Okay, so this matches what the system needs to a control volume. Okay, now if I apply it to what were the conservation equations we learned, we said conservation of mass, conservation of momentum, and also conservation of energy at a later point, right? So similarly, Reynolds transport theorem essentially talks about converting. So the left-hand side, I've just written the conservation equation and the momentum equation like you would know in a normal Navier-Stokes case, like this, okay? So basically, system on the left-hand side, system rule is no net mass generation. Of course, not phase change, normal cases, no net mass generation. So that is equal to what changes in the control volume and then what goes in and comes out, okay? And you also have the momentum case, which is the force. F is equal to ma. So F is equal to two forces, body force, which is your like your gravity force or something like that, and your surface forces, right? So F is here is equal to ma, okay? Mass times acceleration, okay? Or change in momentum. That's what you see here. Okay. So very quickly, what did we talk about? There is always systemic laws of conservation. That conservation is actually converted to your mass, momentum, and energy conservation equations of Navier-Stokes. Why? Because this system law will not apply for a fluid. So they converted that for some fluid that is flowing through a control volume, and you get this structure. Okay? All right. So the next step we have is, fine, this is, all erudite PDE equations, but how do I do CFD with it, correct? So for CFD, always you will have to have a good coding practice. Let me just say that, right? So a good coding practice, if you write a normal Python code or something, and I say, if I is equal to 1 to 100, do this. If I is equal to 2 to 101 to 500, do the next step, correct? Now, does it make sense if I say I is equal to 1, do this, like 1 plus A plus B is this, and then I is equal to 2, same A plus B is this? That's not code, right? You put it in the loop because then let it go figure out and do the loop itself. You won't be writing that in a repeated step, correct? Same way, we have to recognize patterns in mathematical equations to see if you can easily solve it through a loop or through a structure. So, forgetting the fact of these are representations of physics, correct? We talked about, what did we say? This is your momentum change is equal to summation of fluxes, summation of forces, right? That was a momentum equation. That's the physics. But now let's look at it mathematically, because I have to now break it down into common patterns, right? So that's why I'm talking about governing equations from a mathematical perspective. Numerical we'll come to later. The mathematical perspective may ignore the first equation, okay, because that is like a control condition. Okay, am I going 10 steps forward and there is one stop line? Okay, have I reached the stop line? No, I have not. So move again. So that's like a control statement. So mass, is my mass zero? Is my mass balance done? Otherwise, go solve again. So this is like a control problem. But the main equation is, say, your momentum equation, and in some cases, the energy equation, correct? So do you see patterns in the equation? Any one of you? It's momentum and energy, two different things. Do you see a pattern in the equation? Yes, Smriti. Can you be louder? I want to hear you really loud. Smriti.
Sorry, ma'am. So, both the momentum and energy equation, it has a temporal term, like where it's changed with time. It is the first term. And then the second term, I think is the advection term, like how the flux, like mass flux changes.
Okay.
On the right hand side, momentum equation has like various forces like pressure force and gravity force, which doesn't exist in energy. But the diffusion term, like the grad square V and grad square T.
Okay. Okay. Okay, good. Asma, do you have anything to add to this?
Yeah, it's the same thing. It's kind of like, the parameter, the velocity, with respect to momentum, the velocity has been considered over there, while we have the same pattern with respect to the temperature in the energy equation. We have the same gradients and the derivative over there. On the right side of the energy equation, we do not have as many forces as we can see in the momentum equation. That's what I would like to say.
Okay, so see, I think you've got the pattern. So firstly, before going into what is advection and diffusion, the first one, of course, is a temporal term. Okay. Second one has a mathematical operator called divergence, V dot del, right? And of course, these are pressure forces. We can neglect that for the time being. And then you have something called the Laplacian term. Okay. So essentially, you can see that there is a lot of common main math properties. And one would think, why, right? So the reason is basically here you're talking about transport of momentum, and here we're talking about transport of energy. Okay. So if one would just kind of collapse both equations together, you would get a general transport equation. The phi being, you could put U for momentum, and you could also put T for temperature. Okay. And S being the source term. Of course, there'll be one or two other terms, but largely this is your transport equation. So the transport equation now has a temporal term. We will not talk about that for the time being, but we have two main terms, which is, as someone pointed out, Smriti pointed out, it's an advection term and a diffusion term. Okay. So one needs to understand momentum hai, energy hai, but you're talking about something like transport of either of these. So if it is a transport of either of these, what kind of transport? Auto mein baith ke ja rahi hu, or am I sitting in a bus, or am I kind of walking, right? So what is the type of transport that's happening? And that is kind of summarized by either the advection or the diffusion. What does advection mean? Advection means a bulk movement. So if I'm having a fan and I'm blowing air in one particular direction, there's a bulk movement. That's advection. Diffusion means if I just kind of, if you hold a matchstick, strike a matchstick and just hold it, you will see this smoke doesn't, I mean, of course, it rises in the top direction, but there's a lot of dispersive movement, right? So that is called diffusion. Diffusion is largely because of vibrational movement of the molecules. Okay, so this transmission is through vibration and that doesn't have a particular direction. Okay, so either there's a bulk movement or there is a vibratory movement from all directions. And typically movement is a combination of these two. It's not one or the other. It's a combination of these two. Okay, so essentially we have understood that there is advection and there is diffusion. Okay, and they have slightly, advection means you have only del dot something. Diffusion means you will have gradient of the gradient. Why? For example, think of temperature. Particular temperature will only move from high temperature to low temperature if there is a gradient, correct? So that is why grad of a gradient. Okay. So now, once you've talked about this equation, let us look at the numerical aspect of it. Okay. So till now we have looked at the mathematical. What was the mathematical objective? 3 equations, mass, momentum, and energy. Mass is just a control equation. You have momentum and energy equation, which is, it's a transport equation. Once you've collapsed that equation, you identify there are 2 terms, which is diffusion and advection. Now we'll have to handle it numerically. Okay. Yeah, go ahead.
Yeah, I have a question regarding the momentum equation. So you talked about Laplacian. So could you give a brief explanation of what is the Laplacian doing, the Laplacian operator doing in the momentum equation? What is the physical aspect of it?
So when you talk about movement, like I told you, if I'm going to model this smoke that is coming from a matchstick that I've struck and I've kept it, right? Typically, the advective term. So what do you see when you hold it and you hold it up and maybe it goes off, right? It goes off. So you see this smoke plume that is coming up. So typically a large part of the plume will go up, right? So that will be a movement of a directional movement. Why? Because of this natural convection based movement, right? So that will be an advective component. But you will also see strands that are moving in all other directions, which is not really, you will see some plume that's coming down and going up. That is typically local gradients in density, which is going to drive it. Okay. So this difference in a gradient, like a vibratory motion. So the smoke particles are vibrating and they also push the adjacent particles which are stationary. So that movement gets propagated. So what we're talking about in momentum transport is transport where a bulk amount of these particles move up because of the gravity driven differences. The other is because of their vibratory motion, hotter temperatures, they push the additional particles which are stationary into a vibratory mode, and there is transmission of movement. That's what we mean essentially. Is that clear?
Yeah, if I'm right, it's the so the Laplacian basically is talking about the dispersion of the molecules in different directions. Is that what it essentially means?
It is a dispersion of the momentum.
Okay, momentum. Okay.
It is dispersion of either the momentum or the temperature.
Okay.
Ma'am, is there any necessary for energy equation if the flow is considered as isothermal?
Right. So, see, the reason we take a temperature difference kind of expression is it is easier to visualize. Okay. But in the absence of temperature also, a momentum equation will see both advection and diffusion movement. A very easy way of seeing this is if you in a flowing river, if you just let a dye streak go through, you will see that it will not just go down the advective direction, it will also disperse in other directions. That is another indication that there is also diffusion as well as advection. Okay, was that your question? I was not sure.
No, ma'am. No, no.
Go ahead. What was your question?
Ma'am, I'm saying that if the flow is considered as isothermal, then is there any necessary of energy equation for that property?
No, sorry. When you said isothermal, I thought your question was without the energy equation is momentum valid. If isothermal, you don't have to solve the temperature equation. No.
Okay. Thank you, ma'am.
Yeah. Okay. So now moving forward, let us come to I probably have about 10, 12 minutes. Okay. So when we are now looking at these equations now in mind, mainly the transport equation, right? We'll have to now see how CFD is going to solve it. So the first part of the solution is I have equations which I have to solve. But what is the control volume that I'm going to solve it under, right? So the smaller the control volume, the more accurate your solutions are going to be. You will understand why. So at a later point in the talk. So for it to be small control volumes, that means I should do spatial. So if this is a room that I'm sitting in and I'm interested in the airflow, it will obey the conservation equations which I'm talking about. But the point is, if I just divide it into 5 big boxes, it will not be accurate, right? So I'll have to kind of divide it into smaller boxes, which is called spatial discretization. Okay. And in all these small boxes of the room, I will solve the conservation equation. So this first step of dividing a domain into smaller control volumes is called meshing. Once you've done the meshing, you will solve the governing equations, this transport, mass, momentum, and energy equation in each of these control volumes. Now, when you're solving in each of these control volumes, what happens is it's a PDE, right? A partial differential equation. A partial differential equation is essentially an equation which says at every micro point, the equation is valid. But I have a finite sized control volume, right? So essentially, I will have to integrate that equation to apply to that entire control volume. We will see how. Correct. So first step is dividing it into smaller boxes, the domain, then applying whatever equation I have to for that entire control volume. Now, even if I do that, I still have a kind of a differential form, right? And a computer will not understand how to go ahead with it. So I have to convert it into an algebraic form, right? So these are the 3 steps in any CFD. Okay. So now let's take an example. So I've just taken a 1D steady state equation. Okay. So when I say 1D steady state, then you have the conduction equation, which is d by dx k dt by dx plus the source, right? So this is only your Laplacian term because we know conduction is mainly only diffusion. There is no advection. Okay. So we have, say, a rod, and I have divided it into 3 control volumes. That is the first step, which is meshing, right? And the second step is writing the PDE equation, partial differential equation. And the step is I have to integrate this, correct? So if I'm going to integrate this, right, and I already answered the question that this is diffusion, right? So if I have to integrate it, I have to integrate it from one place to another. What did I say? For the entire control volume, correct? So if this is my rod, right, and I have a control volume, say P, Okay, I divided into 3 control volumes. So let me talk about the central control volume. Okay, and the control volume to the left is the west control volume. The control volume to the right is the east control volume. And you have the present P control volume that you are actually interested in. Okay. Now, I divided into 3 cells. So the control volume will have faces, right? Boundaries. The boundary of the control volume is depicted by the yellow line. Okay. Now, between the present P, center point of the cell, and the center point of the next cell, this boundary lies. So I will call it the east boundary because it's between P and E, right? So I'm calling it with a small e. Similarly, the west boundary will be a small w. Okay. So what did I say? First, you write the PD equation, but then you will have to apply it for the entire control volume. So I'm integrating it right from the west wall to the east wall. Correct? Left to the right. Full control volume I'm applying. Okay. This is only one dimensional, not two dimensional. Okay. So I have this equation which I am now having to integrate. Now, if I integrate d by dx of this into dx, this will just come out, right? So k dt by dx, upper limit minus lower limit. So upper limit is the eastern face, lower limit is the western face. K dt by dx plus, now this term s delta x. Dx is actually delta x because this is the length of the control volume distance, delta x. Okay, s delta x is equal to 0. So now we've got somewhat of an algebraic, but there are still differential terms there, right? So now I go on to, this is the equation that I have. This is the control volume. So now let us look at the first term, which is k dt by dx at the east face. East face is this yellow line, right? So I want dt by dx of that face, right? So then I take an approximate. I don't know the gradient or change in t in the x direction right at this face. I only will know here at this central point and this central point, right? So then I make an assumption of a linear gradients. This is where the assumption lies, which is why smaller the control volume, more accurate will you be. If you have a large control volume, it will not be a linear variation, right? Smaller control volume, I say TE minus TP by delta X. The smaller delta is this distance, okay? So I take this minus for the west wall also, I do the same thing, okay? And then what do? I just open up all the brackets and combine all the TPs together, TEs together, TW. Coefficients and all I've clubbed together. That's all. Now this is an algebraic equation. And what are the coefficients? Coefficients are the thermal conductivity and the distance between the cells. Thermal conductivity, you know, of any material. And the distance is your choice, right? You're dividing it into a control volume. So this is mainly a constant. So APTP is equal to AETE plus AWTW plus B being the S delta X, the source. So this is an equation for one cell. Now you will have several cells, so you will have a system of equations. So now we have only looked at which term? Diffusion term, correct? Because this is a 1D conduction alone. Okay. Now, for example, I am not interested only in conduction, but the temperature or whatever. There is the transport equation, which is having advection and diffusion, correct? So you will have, I'm ignoring the temporal and the source term for now. So you have the advection and diffusion term together, one in the left, one in the right, right? So similarly, I will be writing the integrated form of it. That's the first step, from the west end to the east end, right? Lower limit to the upper limit, okay? And I am integrating it. When I integrate d by dx of rho u phi, only this rho u phi will come out. Upper limit minus the lower limit equal to, similarly d by dx of this one will come out. This is diffusivity or whatever you want to call it, d phi by dx, east minus the west, okay? So when I finish the integration. This is my form. Now I need phi. Phi can be anything, temperature or velocity, right? For now, let us look at the perspective of temperature maybe, right? So phi E meaning at this, what is the temperature? In the previous case, what did you see? dt by dx. That is this one. So you need gradient dt by dx, but in this case, I need t. Okay. So t means then I am taking a average. Tp plus Te by 2. This is again an approximation. Okay. And I've made a choice or a scheme choice for this. And I have taken Tp plus Te by 2. And when I substitute this you already know how to calculate. By linear approximation is one approximation. I will open up, combine all the coefficients together, and I will get an algebraic form. So what are we saying? Advection के लिए एक approximation है. For diffusion also you have an approximation, and these control your errors in your CFD code. Okay. So what is the recap of the procedure? First is write down your equations. Correct? System, from a systemic equation, you have to convert it into a control volume equation. Okay. Which is your mass, momentum, and energy. Then you will apply the finite volume method, that is FVM, because you're working with control volumes, right? Where you will start to first mesh the domain. Then you will have integration of the governing equation that you have written. And then you will bring the algebraic equation by making choices for the advection and the diffusion schemes. And then you will get a system of equations, because that's not one cell, there's going to be n number of cells. So when I say system of equations, what will happen is you will get a matrix, right? APTP is equal to AETE into B, correct? So what will happen is you will bring all the coefficients to one side into this A matrix. T will be your unknown, is equal to B is your source term. So you will get some matrix like this, okay? And you will have several such matrices, one for the U, one for the V velocity, one for the Z velocity, then one for pressure also. So you will have several such matrices. So then comes the matrix solver choice, okay, which is already default in OpenFOAM, but as you become more and more advanced, you will know how to solve these, what solver is best. Okay, there are some guidelines also. So this is this entire procedure for CFD. Okay, when you're writing a code. Now in OpenFOAM, this is going to be your case file. You will see in the coming sessions. The main thing is you will have the main case file. Case file, there will be a zero file. Zero file means initially what is the system? Everything is zero. Initially zero, and then I start the fan. Something like that, right? So initial conditions you will set. Then you will set constant conditions. What are constant conditions? Like thermal conductivity, properties, no? Transport, turbulence properties, something like that. So there is a zero folder, which is obvious initial condition. Constant folder, right? And then there is called a system folder. 3 main folders. Under that you will have some subfolders. So there's a system folder. Okay. Now this is the most important folder because you have 4 main things. And it maps on to whatever lecture I just gave you. First step was what? Meshing, right? So you have the block mesh file. Okay. Next thing was what? You have to set some choice of equations, correct? Choice of equations, and time step initial condition kya hai, time step kya hai, all of that, boundary conditions kya hai, all of that is control dict, choice of the problem. Okay. Then you choose approximations, which are schemes, which is FV schemes. And then you will choose matrix solvers, which are FV solutions. So the 4 map on very logically to the CFD methodology: block mesh, control of this problem, what are the governing equations, what are the boundary conditions, schemes or approximations, and then FV solution. Okay. So is the procedure of CFD clear? Number 1. and where to look for what control in open form, you now know. So it is very important you understand this background. Only then you will understand today's the important nitty-gritty points of the bottom point. And I will stop here. So we are good. So good luck. Have a great day today. And please ask questions, because then it makes your understanding more stronger. Okay.